Okay, so I came across this question and there is so much detail to it. And if we may check last year's question paper, it had graphs, which means now they'll want to do or use more questions with graphs. So we need to be able to interpret more of these graphs and understand scenarios as stated from the statement. So question 6 is from Vertical Projectile Motion, also known as VPM, whereby a ball is thrown vertically downwards from the top of a building and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is thrown up to a certain time t. The downwards is taken as positive and the ground is used as zero reference. The graph is not drawn to scale, the effects of air friction are ignored. Well, the velocity time graph, easy to read, as you can see from left to right. It's a straight diagonal graph going up with an initial or starting velocity, which will be initial velocity, and then it ends at some point. So this one is starting here at 10, goes up to 29.6, and then there is a jotted line. That means it might be bouncing or hitting on something. Then after a certain couple of seconds, it starts again at point X, which means this is velocity now, going all the way up to time 4.95. Then it gets to a velocity of a positive 27. Does the bounce again? That's the dotted line. Now, at 8 seconds or 7.1, hits the ground. Then at 8 seconds, now it does what? It moves away from the ground. So it goes all the way up to time t. Alright, I did 6.1 up to 6.5 on my own. But first, the best thing to do when dealing with a question like this is to have a scheme of some sort. So they said a ball vertically thrown downwards, and the ground is used as reference. As from the graph, vertically thrown downwards, hits the ground. Then, after hitting the ground, ball leaves the ground. Now, there is a time difference here, and from which was very vertically thrown. Goes up to a certain maximum point, then gets back down. Hits the ground. After some time, it moves up, or it does what? Let me check again the question. Okay, ball hit the ground and left the ground, reached maximum height, then returned back and hit the ground again. So hit the ground again, and after hitting the ground again, went to maximum height, or went to a certain height. So it's safe to say this would be the last position, I think. But here we're not tasked to draw the position time graph. I think maybe I'll have checked it before. So let's maybe focus mainly on the question because I don't have a memorandum of this. I want to just verify if I am speaking what should be said. It says write down the speed with which the ball is thrown downwards. So the ball started being thrown downwards with a velocity from the graph. It says what? Velocity 10. So 6.1 V initial is equals to 10 meters per second. 6.2. All parts of the graph have the same gradient. Give a reason for this. 9,8. All right. The gradient is change in velocity over change in time, and it is an acceleration. Since we are told that it's constant, that means 9,8 meters per second squared. Why? The whole motion is under gravitational acceleration. Right. 6.3. Calculate the height from which the ball is thrown. The height from which the ball is thrown. All right. 6.3. Height. Ball thrown with the velocity 10. Downwards is positive. Ball is thrown, hits the ground. From the graph, they say it hit the ground with a velocity final of 29.6 meters per second. This one meters per second. We are looking for delta y, and the time it took, let's check the graph again. The time it took for that whole thing to happen, for it to hit the ground, was 0 to 2 seconds. So time taken here is 2 seconds. Therefore, we might look for a formula of which there are two that can combine these four variables. Alright, I'll start with the first one. The first one being delta y is equals to Vf plus Vi over 2 delta t. And we have 29.6 plus 10 over 2 multiplied by 2. Then we get 39.6 meters. The second one is Vf squared equals to Vi squared plus 2a delta y. Now, Vf squared minus Vi squared is equals to 2a delta y. And if we divide both sides by 2a, we get that delta y. Well, this is not advisable to use this mathematical method. It's best that you substitute straight from Vf squared and you're left with numbers only, so that it's easy to do the division. I'm just doing it because I found it quicker. So this is 29.6 squared minus 10 squared all over 2 times. We said downwards here there is a positive 9.8 meters per second squared. So positive 9.8. That'll give us, if you punch it in a calculator, 39.6 meters. Right, that is 6.3. Then we have 6.4. Calculate the time t shown on the graph. Now that is the time for the whole of the bouncing to happen, or the scenario. If we look at it, they told us that all parts of the graphs have the same gradient. So I thought I should use my mathematics in order to solve this one. All parts of the gradients have the same gradient. That's what the statement said. So, which means we have these parallel lines, and all of them will have the same gradient from mathematics. So the first motion, in the first motion takes place and it's a point where x is 0 and y is 10 and ends at where x is 2 and y is 29.6. In that regard, we'll have to calculate our first m1, which is the gradient, using the gradient formula, and substitute these to 9.6 minus 10 all over 2 minus 0. We get our beautiful 9.8 as a gradient. That means it's our acceleration. And in the last instance, we have our short graph that starts where x is 6, where x is 8, and y is minus 25, all the way up to where x is t and y is 0, so that we get m2, which is y2 minus y1 over x2 minus x1. Oh, I forgot to label here. I was in a rush. I normally label this as my x1, y1, x2, y2. Right, next one here, I would do x1, y1, x2, y2, so that we will have m2 being what? 0 minus negative 25 over t minus 8, and that gives us a positive 25 over t minus 8. Alright, while we're there, that is our m2. Remember we said those lines are parallel and they have the same gradient, so which means m1 will be equal to m2, meaning 9.8 will be equal to our 25 over t minus 8. Now, with that being said, we'll have to divide this one by a 1, and then we cross multiply, and then we get 9.8 t minus 78.4 will be equal to 25. That then gives us 9.8 t is equals to 25 plus 78.4. 9.8 t is equal to 103.4. And then if we divide on both sides by 9.8, we get t is equal to 10.55 seconds. And that is how mathematically, because they did not govern us to say use only equations of motion. So now there is a method, but for me, I decided to use mathematics. So I can look for an alternative method for using equations of motion, but for this case, I'm just gonna go with the flow. Right, 6.51 before I wrap things up. Write down the time that the ball is in contact with the ground at first bounce. So the ball is in contact within these two dotted lines, the first two dotted lines. So that's 6.5, 6 comma 5 comma 1. That is delta t will be equal to 2.2 minus a 2, which is equals to 0, 0.2 seconds. That's the time the ball was in contact. 6 comma 5.2. Right, 6.5.2. Let me check quickly. The time at which the ball reaches its maximum height after first bounce. The time it took. So from that point X, we have the time being 2.2 up to when the velocity is 0. Remember, maximum height, velocity is 0. So when velocity is 0, the time is 4,955. Therefore, what they are looking for here is delta t is equals to 4,955 minus 2.2, which gives us 2,75 seconds. 6.53. This one was a tricky one, whereby they say write down the value of x. They did not say do not calculate, but write down. And I went for the best option to say, okay, there is x, which is when it's leaving the ground, up to 0.0 when it's at maximum height. Then I decided, let me use that and use equations of motions, because there is no rule that said don't do this or don't do that. Right, 6 comma 5 comma what 3. V initial is x, V final is 0 because it's maximum height. And acceleration there is now negative 9,8 because downwards is positive. Ball was going up. So the time it took is what we just calculated, the 2,75 seconds. So we're going to find a formula that has all these four, which is Vf is equals to Vi plus A delta T. Right, if we substitute, 0 is equals to x plus negative 9,8 multiplied by 2,75. Right, when we try and solve for x here, we get that x is equals to 26,95, which makes sense because, all right, x is not necessarily 26.95, but x is negative 26,95 downwards. So it means maybe we should have kept our acceleration to be just a positive because it's going downwards. It wasn't actually defying. Acceleration was actually downwards. So we'd have to put this one as a positive so that we get our negative here, because acceleration was still taking the ball downwards even when it was going up. So sorry about that. The last question is asking about, I think I'll just explain that one and not write it down for time constraint. Um, is the collision of the ball, is the collision of the ball with the ground elastic or inelastic? Give a reason for the answer using the information on the page. Right, so there is an instance whereby the ball and the ground collide, stick together, then move away after a certain period of time. So it's impulse momentum. I'll have to cut this video short.